Picture a quiet Sunday morning in October 2022. A flash of light from a dying star 2 billion years away races toward Earth. That light slammed directly into a fleet of automated telescopes in orbit. The radiation was so intense that the detectors saturated. They went blind, overwhelmed by a massive flood of gamma rays. The blast hit with such force that it physically disturbed Earth's ionosphere for hours. Down in India, detectors calibrated to catch local lightning lit up, fooled by a storm raging in an entirely different galaxy. If a burst of this magnitude had gone off in our own galactic neighborhood, aimed right at us, it could have stripped away the Earth's ozone layer in seconds, exposing the surface to lethal ultraviolet radiation. Because that violence was diluted across 2 billion light-years of empty space, we were spared the catastrophe. We got to study a massive cosmic signal safely, and what astronomers found hidden inside the data immediately sparked an intense debate. About 5 minutes after the initial blast, researchers combing through the wreckage found something hiding in the spectrum. Lasting exactly 40 seconds, it was a perfectly clean signal. In the explosion's light spectrum, the data suddenly shoots upward into a single sharp spike near 12 million electron volts. Ordinarily, light spreads smoothly across many energies. This isolated line is rare, a strict chemical signature revealing specific particles reacting. Independent teams checked the data for sensor hiccups or false echoes, and the odds of random noise faking a spike this precise are less than 1 in half a billion. We are looking at a real signal, but one written in a language we have yet to translate. The most straightforward reading of that line points straight to antimatter. Specifically, electrons winking out of existence as they collide with their mirror twins, positrons. When an electron and a positron annihilate, they convert their mass entirely into light. That reaction consistently releases an energy of exactly 0.511 million electron volts. It is a constant of nature, as reliable as a heartbeat. But the signature we caught from the burst peaked at 12 million, more than 20 times higher than the natural antimatter signal. To close that gap, you need blueshift. A light wave physically compresses into higher energy frequencies when hurtling rapidly toward you. A plasma jet blasting toward Earth provides this blueshift, stretching the 0.511 signal until it hits exactly 12 million electron volts. The math supports a staggering conclusion. We may have just witnessed the largest antimatter annihilation event ever recorded. Then another group of researchers looked at the exact same data and noticed a complication. Over the course of a minute, the signal did not hold steady. Here is a chart tracking the peak's position over exactly 1 minute. Notice how the spike physically slides downward, starting at 12 million electron volts and dropping to roughly 6 million before fading away completely. Antimatter annihilation is a rigid process. Asking it to smoothly slide down the energy scale like that requires a highly convoluted set of physical conditions. But an entirely different nuclear reaction fits perfectly. In the extreme heat of the jet, free neutrons collide and fuse with protons to build heavy hydrogen. That specific fusion always releases a photon at 2.223 million electron volts. As the jet plows into surrounding gas, it slows. We track the blueshift boost factor dropping from 5.1 to 2.1, naturally dragging the observed line from 12 down to 6. We are left with one massive puzzle and 2 mathematically sound explanations. We either glimpsed a colossal jet of antimatter winking out of existence, or we watched the simple fusion of ordinary neutrons. The bizarre physics of the jet is only part of the story. Trace the source of the burst backward, and you find a collapsing star that defied another major expectation. Astronomers pointed the James Webb Space Telescope at the fading supernova, analyzing the infrared light to look for the creation of new elements. Current theory dictates that catastrophic stellar collapses are the cosmic foundries of the universe. They are supposed to be the main source of heavy elements, like the gold hammered into a wedding ring. They are also thought to be the birthplace of denser industrial metals, such as the platinum required inside an automotive catalytic converter. But when the spectral data came back from the supernova, the signature for heavy element creation simply was not there. The brightest blast on record failed to produce the materials it theoretically should have. Either the metals are hidden from our view, Or our long-held models for how the universe manufactures its heaviest elements have a major gap in them. A collapsar this intense leaves a permanent mark on the surrounding void, wrapping a violent engine in a swirling shell of gas and dust. We are left staring at a record-breaking flash, an oddly shaped jet, a supernova missing its expected gold, and two rival subatomic theories fighting over a single line of light. Beyond the blinding brightness, the boat's lasting gift is the way it exposes specific, measurable gaps in human astrophysics. It forces us to reconcile our current theories with data that simply refuses to cooperate. Every time we build an instrument capable of looking deeper into the dark, the cosmos responds by handing us a puzzle that breaks our established rules. We trade our comfortable theories for vastly more interesting questions. If you enjoy standing on the edge of the unknown, consider subscribing to keep exploring the universe with us. And let us know in the comments, which unresolved mystery of the universe keeps you awake at night? Until next time, always keep looking up.